Welcome to the Deep Dive.
You think finding something in your junk drawer is hard.
Try searching for a brand new particle in data from the Large Hadron Collider.
That's what we're looking at today.
How scientists are using quantum computers to find anomalies in particle physics.
It's a cosmic needle in a haystack.
And joining me to talk about this is expert speaker, our physics guide.
Hi.
So, expert speaker, what exactly is the Large Hadron Collider?
I'm picturing something huge and powerful.
Yeah, you're right.
It's the world's biggest, most powerful particle accelerator in a 17-mile loop underground.
Like a giant microscope, but instead of light, it smashes particles together at almost the speed of light.
Okay, that's already blowing my mind.
Why smash particles together?
What are we hoping to see?
The goal is to recreate the Big Bang.
Well, on a smaller scale, of course.
We study what happens after these high-energy collisions.
Physicists hope to unlock secrets of the universe, like new particles and forces.
Things that could change how we see physics.
So we're smashing subatomic piñatas and studying the candy that comes out.
Looking for that one unique piece.
That's a tasty way to put it.
But here's the thing.
The LHC creates tons of data, most from things we already understand. Background noise.
Finding evidence of new physics, groundbreaking stuff, it's like hearing a whisper at a rock concert.
That sounds so hard.
How do physicists handle all that data?
That's where anomaly detection comes in.
Imagine a computer program, a master detective, finding anything unusual in the data.
Things that don't fit.
These anomalies could be clues to something totally new.
So instead of reading through mountains of data, physicists use computers to play detective.
Exactly.
And one of their best tools is called an autoencoder.
Think of it like a high-tech magnifying glass.
A magnifying glass, huh?
Tell me more.
How do these autoencoders work?
So a classical autoencoder, it looks at the data and tries to make a simple blueprint.
Showing the most important patterns.
Then it uses this blueprint to rebuild the original data.
If the reconstruction is good, great.
It means the data is probably just normal background noise.
But if the reconstruction is really different...
That's our detective shouting, "Eureka!"
Right.
That mismatch is a sign that the data doesn't fit and could be something big.
Brilliant.
But where do these quantum computers fit in?
Are they like super-powered magnifying glasses?
You're getting there.
Quantum computers are fundamentally different from regular computers.
Imagine they have special X-ray vision, seeing hidden connections in the data that regular computers miss.
They use quantum mechanics to do this.
Okay, that sounds really powerful.
How do they use this X-ray vision for particle physics?
Well, these quantum autoencoders, or QAEs, they might be really good at finding small quantum correlations in the LHC data.
Relationships that could help us find new particles or forces?
So they're like super sleuths of the quantum world.
That's a good way to put it.
That's incredible.
And here's more.
The research you sent shows some cases where quantum autoencoders really stand out.
There's more.
Don't stop now, expert speaker.
Tell me everything.
Okay, imagine a particle physics arena.
Where we have these quantum autoencoders.
And they're up against the classic ones.
Okay, a science showdown.
What are the challenges?
So in one corner, there's the classical autoencoder,
It has to find a heavy Higgs boson.
which is decaying into top quarks.
Top quarks.
Remind me about those.
Right, so top quarks, they're like the heavyweights.
The heaviest of the fundamental particles,
Super important for understanding the universe.
but really hard to find.
Like a rare gem.
Yes.
And our classical autoencoder, it has to tell the difference between this Higgs boson decaying into top quark.
And regular top quark pairs.
So it's not just finding a needle in a haystack.
It's finding a specific needle in a haystack of similar needles.
Exactly.
And then in the other corner,
A quantum autoencoder.
it has to find the Higgs boson, but decaying into dark matter.
Dark matter.
The stuff we can't even see.
Yeah.
And because we can't see dark matter, we can only detect it by its absence.
What we call missing energy.
Like if I throw a bowling ball.
And some of the pins just vanish.
Perfect analogy.
So the quantum autoencoder is looking for that missing energy.
That suggests the Higgs boson decayed into dark matter.
All right, so we have our contenders.
We have our challenges.
Who won?
Drum roll.
In both cases, the quantum autoencoders were better.
Really?
They beat the classical ones.
Yes.
They were much better at finding those little hints of new physics.
Can't all that noise.
Like a Sherlock Holmes of particle physics.
Wow.
Were there other advantages?
The most impressive thing to me was how efficient they were.
These QAEs were really accurate.
Even with much less training data than the classical ones.
Though they learn faster too.
Exactly.
And in particle physics, getting enough data can take a really long time,
These quantum autoencoders, they could speed things up a lot.
like a fast-forward button for science.
But is this real or just theory?
Well, it gets even more interesting.
The researchers, they actually tested a small quantum autoencoder.
On real quantum hardware.
Wait, a real quantum computer?
Yep.
It's still early days.
But getting good results on real hardware is a big step.
So we're not just talking about science fiction anymore.
This is really happening.
It really makes you think about what else is possible.
But what does it all mean?
How do these quantum autoencoders change the big picture?
This is wild.
But I have to admit,
I'm still trying to understand what it all means.
like, I get it.
We're talking about maybe changing the laws of physics.
But how does this affect me every day?
Does finding a new particle, even one as cool as the Higgs boson, change anything for people?
That's a common question and a good one.
It's easy to focus on the excitement.
And forget about how it actually affects us.
Think about when electricity was discovered.
Back then, it was just a curiosity, a novelty.
No one knew it would change everything.
Light bulbs, telephones, computers, the internet.
It's like those gadgets you see on TV.
They sound amazing, but do they actually make life better? Big scientific discoveries are like planting seeds.
We may not see the results for years.
But they have the potential to transform our world in ways we can't imagine.
So no charging our phones with a Higgs boson soon.
But it could lead to new technologies that change how we see the universe.
Exactly.
And the best part is, this is just the start for quantum computers.
It's like we've got this powerful new tool.
And we're still learning how to use it.
Like we're being given a spaceship.
Before we even know how to drive.
Ah,
What a time to be alive.
makes you wonder what other mysteries are out there.
That's what's great about science.
Always something new to find.
Every answer leads to more question.
Again, we keep pushing the limits of what we know.
And maybe someday, thanks to quantum computing,
And brilliant minds like you.
we'll finally unlock the universe's biggest secrets.
That's the hope.
Expert speaker, thanks for joining me on this deep dive.
It's been amazing.
It was my pleasure.
And to everyone listening.
Thanks for sending us this awesome research.
We hope you enjoy learning about quantum anomaly detection.
Until next time, keep exploring, keep asking questions, and keep that curiosity alive.